getting the Tegra line into as many robots as possible. So we'll begin with a review of what robots look like in the modern era. I think there are a lot of conceptions. The Jetsons, for example, which our dev board is named after, give a lot of sort of dramatic and inspirational ideas of what robots should do in the household, in the workplace, and in other everyday environments. So I recently attended a conference in Chicago in which a lot of vendors were basically displaying their most advanced offerings. And this is a pretty cool robot. This is a research robot that focuses on arm manipulation from a company called Android and Robotics, founded by iRobot's former CTO, Nick Roomba. This is sort of a very inspirational robot to the community. It's designed to be a budget research platform, so it's actually around $25,000. That counts as budget in the world of academia. And then we go to something more professional. So this is actually a Tesla Motors factory in Fremont, California. And these robots are obviously on an industrial scale. They're made by a company called KUKA out of Germany, not far from Munich. And these robots are notable because they're capable of interchanging their hands. Tesla is still making cars in fairly low volume, so robots need to be multi-purpose. And so these robots, instead of picking up a tool out of a box, they can actually replace their hands with different types of hands that perform different functions. So just as Nvidia has enterprise applications and defense applications, very large-scale applications, this is KUKA's large-scale application. And this is their Jetson. This is U-Bot. This is, again, in the $25,000 price range. This is another arm manipulation platform. So you can see a little bit of the, the relationship to the large-scale industrial robotics here. But this is, again, designed for universities to work on computer vision and manipulation algorithms. So now we go to something called the PR2 and Willow Garage. So Willow Garage was a pretty groundbreaking organization in the field of robotics. It spun out of Stanford and basically collected a lot of talent from all around the world. And primarily, they worked on this robot that you see here called the PR2. Unfortunately, this is no longer manufactured. But this was sort of a test platform to integrate OpenCV for computer vision and ROS, the robot operating system. Basically, Willow's mission statement was to eliminate all the heartache and challenges of getting a robot off the ground by giving people an easily distributable and reproducible set of packages on which to build things like computer vision, manipulation algorithms, all using a standard set of protocols. I'll get a little bit more into that later. And basically, this is what's left of Willow Garage. A lot of the employees have split to Facebook and Google and the big players in the Valley. But thankfully, we're left with a very nice entry-level robot. This is a $1,500 robot now sold by ClearPath Robotics. And this is a little bit endemic of what happens in robotics today. A lot of times it makes sense to mount a laptop or embed a full x86 PC in your robot because ROS is effectively best supported on this platform. They're pretty established Connect and OpenNI drivers for doing depth processing. So if you really want to explore all that the world of robotics has to offer, this is a good place to start. And again, you wouldn't need a 5-figure budget like the universities have to purchase professional tools. So now let's go to the chip that Nvidia has been manufacturing and you've seen on display today and yesterday. So just to give a little bit of a rundown. I'm pretty impressed by this chip, in part because, as far as I'm aware, it's the fastest quad-core chip on the market when you're talking about the ARM architecture. And it's also the only one to include the best that Nvidia has to offer in terms of graphics processing. And so I'm not sure if you guys are all familiar with CUDA, but CUDA is an architecture that allows you to execute massively parallel, basically, I don't know what you'd call them, processes, I guess. So if you want to do image processing and you want to process a whole frame at once, or you want to process 16 or 96, or in this case 192 pixels at once, you can do that with this tool set. And that's the type of thing that gives an order of magnitude speed up for things like computer vision and image processing. And so, today and yesterday you saw the Shield tablet, which we had on display, and that includes Tegra K1. And so that's basically an Android device, but we also ship an Ubuntu device as well. So, and the other key factor about this chip is that it generally uses no more than 5 watts. I guess I've been pretty upfront so far that if you do absolutely use every single CUDA core and leverage every single function on the chip, then you can maybe hit 10 or 11 watts. But on a robotics platform, that's still reasonable. You can even get that like airborne. Doing 10 watts on a quadcopter drone is perfectly reasonable for a lot of people in industry. So here's the full set of products that have shipped so far with the TK1. The Xiaomi Mi Pad was pretty popular in China, actually. It never really made it to the West, unfortunately. But that allowed us to launch the Shield tablet, which we think is a wonderful flagship device. And then sort of the asterisk on the TK1 project is Google ATAP's Yellowstone Tango tablet. Google put a lot of effort into this device. Doing depth imaging on any kind of mobile platform is challenging, as I've sort of alluded to. Google has done a great job integrating depth sensors and RGB cameras into a form factor that's quite similar to the Shield tablet. They previously had a mobile phone form factor device that they used a custom ASIC to actually do a lot of the depth imaging and 3D reconstruction. Now we're actually able to do it on the TK1 itself using CUDA. So that allows flexibility. You can actually push updated code. You don't have to reprogram an FPGA or an ASIC or upload a new firmware. You can just, even through an OTA update, push new CUDA code to the device, which is pretty impressive. So now we actually get to the dev board. Basically, this is the core of my focus at Nvidia. And this embeds the TK1 with a lot of peripherals and pinouts and headers to give you, as an end user, a lot of flexibility in prototyping a device. Just to go through a brief feature summary, I won't read off all the interfaces, but the first set is what the full-size connectors give you on the periphery of the board, and the second set is what you see on that GPIO header. And we actually discovered a guy in Hungary did a great job sort of annotating all of the functionality of the GPIO header. And this device, as I mentioned earlier, ships with Ubuntu 14.04. So while the other Android devices that have shipped on TK1, they've all focused on Android, this device ships with 14.04, and that's what Nvidia is engaged with. We've released a lot of Linux 4 Tegra code to facilitate different types of distributions going forward. And I was especially impressed when I booted up this board for the first time and I could run the Unity desktop environment fully 3D accelerated. I felt like I was on x86. I mean, there were a few packages I couldn't install that I might want to work with, but for the most part, it felt like a fully featured desktop system, which I had never experienced before on ARM. And a lot of you have asked what the availability of this board is, and a couple of you recommended that I go to Maplin to pick up some soldering supplies a couple days ago. And so that's the price point for the UK, £199. And then the last point on this slide is a little bit of a footnote because NVIDIA doesn't officially internally support this. But I'll just jump ahead here. Here are two rough screen grabs. You can see KitKat on the left, and you can see CyanogenMod on the right. And I invite all of you to investigate and support us if you'd like. And then here's another pinout of all the peripherals that we have on the board. Okay. So moving on, if you're going to build a robot, and that's your goal, leveraging robot operating system is a good way to go. And I think going forward, you'll see a lot of projects that integrate ROS with the Jetson board. And this is a key example of why you might want to use ROS. This is a presentation given at ROSCon a little over a week ago. And this is a researcher from University College London who basically took imagery of a field near his offices and basically put it into this system called Gazebo and then rendered it with a tool called RViz. And unfortunately, he had a video that had a whole flock, a swarm of drones. This image only has one. But basically, the robot can be aware of where it is sort of in its surroundings. And as a human, if you want to visualize this, you can even apply textures and imagery. So this is a pretty robust package in terms of understanding your robot and understanding what your robot understands about its environment. And the nice thing about ROS is that it's pretty common practice for a lot of people in academia. They write these incredibly complex and advanced research papers, but then a lot of times it's somebody else's job to integrate that into a robotics stack. And luckily ROS sort of encourages people in academia to upload their code to GitHub and create ROS nodes, as they're called. And nodes are basically the most fundamental component of ROS. So this is an example of, so this is RViz, but I mentioned depth cameras a little bit. This is an example of reconstruction in real time. And this is generally a process that's fairly fast on x86. It's even faster if you upload some of the rendering and reconstruction to the cloud. But it's actually quite workable on Jetson TK1, and we believe you couldn't do this on Raspberry Pi, you couldn't do this on Arduino. Those are great platforms with different use cases. We believe this is sort of the killer app for Jetson. If you can do this on 10 watts, then you have a really amazing tool set on your hands. And this is another example of ROS working with Tango. So we mentioned the Tango tablet a little bit earlier. This was done with the predecessor phone, but you can see the same RViz tool, which is actually aware of the location, not only the rotation using gyros and IMUs, but also the translation of the device. And the translation is done purely through imagery. The device is aware as it moves and changes its view, where it's actually moving in 3D space. And so this is probably, I can skip forward here. You can start to see trails of where the device is being moved around the environment. So you see you have the pose data as well as the translation data, and this is invaluable for robots. Robots need to know where they are and where they're facing, where they're going, and this is basically all about situational awareness for an autonomous robot. Okay, so I've talked a lot about CV, and CV is super cool. But if once you've discovered that CV is awesome, you kind of want to know, how does it work? What is it? And so I'm going to give a brief rundown. So computer vision is perception, but it's digital, right? When we perceive things as humans, we have neurons, we have all these mental systems to understand our environment. But how do you replicate that, in code? That's a pretty challenging problem. So when we see an image, clearly we understand that there's been a collision, that this is an unnatural situation. But initially, a computer just sees a matrix of data, and maybe a matrix of darkness and lightness, or a matrix of color. But how is a computer going to understand that that's a train? How does a computer understand that the train should not be in a position like that? And there are other challenges to computer vision. I mean, this is the same scene lit from different manners, and a computer vision algorithm that's not robust might understand one of these three pictures, but it won't understand that all three of these pictures are actually the same scene. Here's another example. Background removal is often challenging. Even humans, when I first looked at this slide, I only saw one of the two sea creatures. I don't know if this is a crab or the scorpion. So motion is another issue. And lastly, it's hard for a computer to understand that these are objects of the same class. So this is an old problem. This is a problem probably identified in the 1970s. And ideally, we'd like to think that we've made some progress in the intervening 45 years. And indeed, we have. This is another example of a challenge for computer vision. How does a computer know that an object is occluded or behind another object? And this is an example of the objects that are experiencing collusion. So SIFT was really the first robust tool set to be able to understand what's going on in an image for computers. And basically what it does is edge detection, and it processes the nodes and the vertices and the changes in color and brightness. And the challenge here is, you want this system to be able to identify the same object regardless of location and scale, orientation, and illumination. And that's not a trivial problem. You can see here's an example of SIFT, a SIFT algorithm analyzing features on an image and identifying them in an image where the 3D scene is rotated. And basically, they're attributes of each of these little samples that can be correlated to fairly high accuracy. And this is an example of a system using only black and white data because it's simply easier to process. It's less data to use. And here's an example of the same scene with occlusion and attempting to find features to basically handle the occlusion, to understand when an object is occluded by simply tracking the features that are visible no matter how small they are. And here's an example on an Nvidia device. So here we see, this is basically an augmented reality demo. And so this device is using feature tracking accelerated by CUDA and a package called OpenCV for Tegra, which has other optimizations for the Tegra platform. And then it renders a cube. And so the person who's demoing this is shaking the device because he wants to demonstrate that the response time is low latency, and also when you move the tablet away from where this object is supposed to be, it still knows where it belongs in the 3D environment. Here's an example for automotive systems. So we're all familiar with self-driving cars. Google's been pushing this for quite some time. But some of these features are actually coming to shipping commercially available vehicles, including self-parking systems. So this is an example of feature tracking, again, to some extent using surf, possibly also using depth data to track obstacles and track the environment. And this is a real example where robotics can sort of help situations outside of what we think of as pure robotics. And this is a demonstration using Kinect. So Kinect really revolutionized depth cameras because it made them cheap and accessible to pretty much everyone at a price point of around $150. This is another example of 3D reconstruction, and this is just using depth data. The reconstruction we saw previously used depth and color, and that's why you were able to apply textures to surfaces around you. And this is, I don't know if the audio is going to work on this. So this is actually our tablet on display at Google I/O, and again, it's using depth and color imagery to recreate surfaces and meshes and geometry in real time. So we hope to see this on Jetson in Ross at some point in the near future. So if you want to engage in doing this sort of development, we try and make it as easy as possible. Traditionally, CV has been a pretty difficult science, relegated mostly to PhD students at top-tier universities. But we want to make it accessible to anyone who's tinkering around in their garage, and I think you'll see that improve over time. So this demonstrates that you can actually prototype on desktop, and I've worked for companies where a lot of the computer vision prototyping has been done on desktop, and then it's ported actually to the TK1. Once all the bugs have been ironed out and the code's been optimized, so that it runs quickly on lower power hardware. These are some of the tools that we make available to debug your CUDA code and debug your computer vision code. As you can see, they run in Eclipse, so you could run these usually on an x86 PC that you're developing on initially, although to some extent you can actually run these on the Jetson itself. I have Eclipse installed on my Jetson.
There was no end site for Eclipse before, was there?
I think it's a fairly recent release, so it's separate from the Microsoft Visual Studio tools, but they do have some of the same feature sets. So this brings us back to OpenCV, which we discussed a little bit earlier. OpenCV being maintained by Willow Garage, and it's been developed by multiple parties over the years. There are now contributions from Aldebaran, ITSEs, and these are some of the more basic features of OpenCV. So you've already seen some demos in action, but like I said, CUDA is very well suited for OpenCV because CUDA handles massive data sets. It can handle matrix multiplication, linear algebra, and it can do multiple parts of the matrix in parallel. And so here we have the depth maps, which we've already seen. We've already seen optical flow. We've seen object tracking. We've seen features. Camera calibration, if you actually get deep into robotics, will be a constant nightmare. So it's nice that OpenCV addresses some of these issues. So CUDA, in this case, sits on top of Tegra, and here's basically the entire ecosystem. VisionWorks is a tool set that NVIDIA will be releasing in the upcoming months. Because at the moment we ship CUDA demos, which show things like particle simulations and image processing, but we don't show anything that really demonstrates computer vision. So VisionWorks is NVIDIA's attempt to give sample code and give demos and examples to developers so that they can get started right off the bat with computer vision. And that brings us to another relevant aspect of CUDA for robotics, and that is neural networks. So, if you're imagining working in a lab and you're trying to simulate human behavior, but you want to do it on hardware, you can go to the lowest level and you can simulate neurons. You can simulate aspects of the brain. And people have been trying this, as this slide says, since the 1950s. And there have been multiple attempts of varying success to integrate neural networks into everyday tasks. This is an example of handwriting recognition. I think this was designed for the US Postal Service probably in the 1970s. And this demonstrates all the legwork that a computer has to do to try and read your handwriting. I sometimes have trouble reading my own handwriting, so it kind of blows my mind that a computer can do it. But this demonstrates the feature extraction and the simplification of what a computer sees that it has to do in order to actually process this data. But there are actually more sophisticated examples. So in recent years, you've actually been able to train a system of simulated neurons to recognize objects. And these are examples from a paper out of NYU, I believe, where full objects in a scene are recognized. And you can see some of those difficulties that we saw earlier, like occlusion. And these systems are robust enough to be able to recognize objects despite occlusion, changing lighting conditions. And also just different visual embodiments of the same object. And this is sort of how it works. You present an image to the system, and you can imagine our 192 CUDA cores on the left handling a lot of the parallel processing, including edge detection, including feature detection. And as it goes on, it simplifies the problem into basically buckets that determine whether it's a match with a reference image or not. And that's sort of what's going on here. Here we have a dog presented to the system. And the system is wrong initially. It recognizes it as a turtle. You can imagine a small child misidentifying an object. And then the backward propagation is data associated with the image. So if this image is tagged as a dog, the system can learn that, well, no, it's actually not a turtle. In the human metaphor, the backward propagation occurs when the parent says to the child, well, maybe that looks like a turtle to you, but it's really a dog. And so this is an example of the system being trained with multiple images. You basically pass as many images as you can through the system to eliminate false positives. And so this is an example of this working in real life. And NVIDIA builds several automotive systems that are sort of publicly documented. And this is the underlying research, again, from Courant and NYU. And this is sign recognition. And this demonstrates that, in fact, this system, by some metrics, was actually more capable of identifying signs than humans were. In some ways, this is an easier problem than object recognition because there's a limited set of signs that the system is trained to recognize. Similarly, the system can be trained offline. It doesn't have to learn on the fly. It can be pre-programmed with effectively digital, the equivalent of human memory, but in digital form to understand that, this is a yield sign, this is a speed limit, etc. So computer vision is still challenging. As you've seen, there are a lot of complexities to it. Vision is tough for humans, but it's even tougher for computers at the moment. And this is sort of NVIDIA's relationship to computer vision. We support this on Tesla, which is a desktop graphics accelerator. It's a little bit separate from the normal GeForce gaming-oriented line that you might be familiar with. And we also accelerate this in the cloud. You can submit these training data sets up into the cloud and process all the data and generate the data set you need to accurately identify road signs. And deep learning is another application. It's sort of a hot topic in the area of machine learning at the moment. And again, this is simulating the neural networks that we were talking about. It's having massively parallelized neural networks. The more NVIDIA GPUs you have, the bigger a brain you can have, whether it's in the cloud or in a server in your hallway, or even in an embedded board like the Jetson K1. So all of this is fine and dandy. I think we've sort of addressed the higher end and the academic community and what PhD researchers are doing in the field of robotics. And of course, some of this over time will trickle down into shipping products. A lot of the Kickstarters of today, we've seen sort of a startup hardware revolution in recent years, including significant companies like Oculus being sold to Facebook in the past year. So these are some examples of shipping robots. And a lot of these don't have Jetson on board at the moment. Some of them run on microcontrollers, some of them run on ARM application processors. The market is still very much in flux. And so these are humanoids. This is the Aldebaran Now out of France. Now meaning brain in Chinese. And this is Atlas. I guess this isn't exactly a shipping product, but it's too cool not to put in a slide deck. So Atlas is currently engaged in the DARPA challenge, and there are several companies and research groups using Atlas to execute things like turning valves, lifting heavy objects, things of that nature. But then really the question is, how do I get started? And I don't know, there was one demo that I saw this weekend from a guy named Luca, who built an awesome demo, not only with VR, but it had multiple phones using their accelerometers on a network. And it basically integrated an Arduino as well and used sensors on a plastic gun. And this basically created a fully immersive VR environment where you could aim, move around, and have multiple basically degrees of freedom with different parts of your body, the gun, the head, the body, etc. And something like the IO is a good way to get started if you really just want to use your Android phone and one other device. And then I put Romo up here because Romo is highly visible and has gotten a lot of publicity. This is an XDA event, so I should have put an Android example, but this one's actually more famous. And basically, you can use all the functions of a phone or a tablet, including the cameras, the CPU, Android, and maybe even ROS, to have an interactive device, like you see in this example. So lastly, I said it was early days for Tegra and the TK1 chip in robotics, but these are some early examples of projects we've seen that use the Jetson. And so the one on the left, this is made by a colleague of mine in Australia, and this was the first sort of walking robot with Jetson on board. And it does use computer vision from a standard webcam, like you can see. And then we can go over to GE, who built a tracked robot, and this has actually stereo vision. There are two cameras on there, and I believe they use the gigabit Ethernet interface. You can see Wi-Fi, you can see a SICK LiDAR array. That's a fairly expensive one, but there are cheaper ones available. And then you see Mizar. So Mizar is an Italian project that's been going on. It's used other dev boards in the past. And I can't tell if this one has a depth camera on board. I thought it might have, but I'm not 100% sure. But you can very easily imagine a Kinect or a similar depth sensor on the front of these devices to do some of the things we were talking about before in ROS and RViz, including 3D reconstruction. And then basically we need to look to the future. There are other projects out there, both on Kickstarter on the left and on the right in academia. That's a biomimetic fish robot from CSAIL. And I hope someday I see a Jetson inside of a robot that looks like a fish. I'd be pretty excited. So basically, it's up to you. I think robotics is here to stay. It's inspired imaginations for decades, maybe even centuries. And people talk about the Internet of Things and big data, and I think these are very important trends. Some of them may be fads, I'm not sure, but I think robotics, given the need for logistics, given the need for cheap healthcare, I really think robotics is here to stay, and I think it's going to be a massive industry for decades to come. So I don't know. Do you guys have any questions? Yeah. I think I'm actually not sure. 250 grams, maybe. I need to look it up.
well, being the most powerful system like that, and all these computer vision things, how far, what you will reckon is the delay between pre-processing and putting it on the screen? For example, when you are, I'm especially talking about the positioning,
right.
I'm talking about the arms.
Yeah, so the question was about latency between input and output in robotics devices. And I think that is challenging. I've worked with people who have written computer vision algorithms that might take anywhere from half a second to 4 seconds per frame. And there are a couple ways to address that. The cloud is one of them. You can use clusters of Nvidia servers in the cloud to do some of the acceleration that isn't absolutely necessary for real time. The nice thing about robotics versus something like Oculus VR is that you don't have to be able to sort of turn your head and have an immediate response. Some latency is acceptable for certain situations for robots. I mean, there may be examples, especially with drones, or if you want your robot to be able to catch a ball where response time is super important. In that case, it's just a more challenging problem. It's going to take more optimization on the CUDA front and optimizing your algorithms. I will say that the Jetson is pretty cool because it uses a shared memory architecture. One of the main complaints about people who work with CUDA on desktop is that there's a lot of latency induced by transferring images and matrix data from the CPU to the GPU and then back again. And luckily, we addressed that to some extent on our Jetson board. Oh. So it's actually 120 grams. I doubled my estimate. Yeah?
Are there any plans for x86 processors, including CPU and GPU inside one system on chip?
No comment. So, are there any other questions, or we'd like to do a couple giveaways if you guys are interested. I don't know. All right.